Okay, so for the orbit problem, we're going to deal with a mass little m that's orbiting a mass big M. And up until this point in our careers, we've just focused on circular orbits. Well, we can do a lot more now that we have our cylindrical coordinates. So here's the mass big M, and this one is little m. And then we're going to have our coordinate system. So I'll set up our unit vectors here. So this is going to be, we'll put the origin on the sun, and so this will be the r hat unit vector. And then perpendicular to that will be the theta hat unit vector. But like that. So that's r theta. We are as well going to have another direction, the tangential direction. That'll be defined by the velocity tangent to the curve at this point. So this is r, this is theta. So I'll call this one r hat and this one theta hat. Now in terms of forces, the force on little m will be the inwards force of gravitation, and universal gravity is given by g big M little m over r squared, where r is the distance between the two centers. So we'll write out the force equations. So the sum of the radial forces, well, you've got gmm over r squared in the negative radial direction. Well, I better do that over here just to make sure you see it. So the sum of the radial forces is negative gm little m over r squared, and that's going to equal the mass times the radial acceleration, which is this expression down here if you remember your cylindrical kinematics. And then the sum of the theta forces, well, there are no theta forces, so that equals the mass times the theta acceleration. And then this expression here is the theta acceleration. So that's got to be 0, and the radial acceleration, if you cancel off little m, is got to be negative g big M over r squared. So let's focus in on this theta acceleration. We know it's 0, but we can write this in the following form. The 1 over r, and this will be r squared theta double dot. That obviously reduces to the first term. And then plus 2 r dot theta dot. Remember, r dot and theta dot are just time derivatives of r and theta. And then that will equal 1 over r, and I can write this as the time derivative of r squared theta dot. Now you can just confirm that doing ddt of r squared theta dot gives you this thing inside. This would be leave r squared, differentiate theta dot, get theta double dot. This is leave theta dot, and then do the ddt of r squared. It'll be 2r r dot by the chain rule. Now, because all of that equals 0, so 1 over r times the ddt of r squared theta dot, that is, of course, the theta acceleration, and it is 0. Then, because r is not 0, it must be that this time derivative is 0. And if the time derivative is 0, then that tells us that the thing inside isn't changing with time, i.e. it's a constant. So r squared theta dot must be a constant with time for this orbit. Now, what is r squared theta dot? Well, if we look at the orbit, then we'll see that over time, as the little mass moves, it sweeps out an area. And this is a small amount of time, so this is a little angle d theta. And then by the arc length formula, the arc length here would be r d theta. That's the length of the arc. So it's almost triangular, though. And so we can find the area of this wedge just using a half times base times height. And then the base is r. And the height, this is very nearly 90 degrees in the limit of small theta. So that's r d theta. So that is 1/2 r squared d theta. So that's the area swept out. If you divide that by the infinitesimal time dt, you get 1/2 r squared d theta dt. is 1/2 r squared theta dot, which we just saw above is a constant. So what we've shown is that the rate at which area is swept out is a constant, and that's Kepler's second law, equal areas in equal times. The rate of area is a constant. So that we get from analyzing the theta force equation. We're not quite done yet. Remember that angular momentum is moment of inertia times angular speed. Moment of inertia for the mass little m going around the sun will be mr squared. Multiply that by omega, but omega is the time derivative of theta. So this is mr squared theta dot. Now, if we divide both sides by mass, then you get the angular momentum per unit mass, L over m, is r squared theta dot. And we've just shown, and have been contemplating for a few minutes here, the fact that that's constant. So I'm going to call that something else. I'm going to call it h. Okay? That is an angular momentum to mass ratio, and it is a constant for this orbit. At this point, we'll turn to the radial equation, the R equation. And we're going to try and solve that equation and get an expression for how the particle moves. And this was our R equation. So it's a differential equation involving R and theta. And we're going to, first of all, do a substitution. We're going to change variables. We're going to let R be the reciprocal of U. And we want to try and substitute into this equation for R and R double dot. So first, let's do R dot. That'll be dr dt, so we're differentiating this. We can write that as dr du times du d theta times d theta dt. And dr du, if I differentiate that with respect to u, that's minus 1 over u squared. Du d theta I'll just leave. And then d theta dt is theta dot. So that is minus theta over u squared du d theta. But of course, theta dot. Of course, remember what we said just previously. We said r squared theta dot was a constant, was h. So theta dot is that constant h over r squared. And 1 over r squared, reciprocal of r squared, is just going to be u squared. So this will be h u squared. So when I put that in for theta dot, I see that the u squareds will cancel out. So what I get for dr dt, which is r dot, of course, is minus h u squared over u squared times du d theta, or just minus h du d theta. Now, of course, what I want to substitute into my equation is r double dot. That means I need to do a second derivative. I need to ddt this expression that we just found. Now, h is a constant, so it just gets pulled out. And now I need to ddt du d theta. Well, I am going to rearrange that. I'm not going to ddt it. I'm going to dd theta it, because u depends on theta. But then I'm going to multiply by d theta dt. Now, d theta dt, of course, is theta dot. And theta dot, we can see from up here, is h u squared. And so, this is the second derivative of u with respect to theta. So it's d squared u d theta squared. And then we get an hu squared here times h. So it's minus h squared u squared. Now, that looks like a whole pile of mess, but it ends up making the differential equation a lot easier to solve. So let's substitute into our radial equation and see what happens using this variable u. Now, remember that for this theta dot here, it's going to be h over r squared, which is h u squared. And then we just found for r double dot, it's this expression here. So let's substitute that in. So we'll get minus h squared u squared d squared u d theta squared minus, okay, for r it's 1 over u, and then theta dot squared is that, and then 1 over r squared is going to be u squared. So what I get here is minus h squared u cubed for this term, and then I see u squareds everywhere, so I can cancel them out, and I see minus h squareds almost everywhere, so I cancel them out. So if I divide through by this, I get d squared u d theta squared. That's the only term that survives. Here I end up with a u, and because I'm dividing by a negative, all the minus signs disappear. And then here I end up with a constant. Now, that looks a lot like simple harmonic motion, because a second derivative ends up equaling the function itself. And of course, for a second derivative, we know that cosines and sines work. So let's substitute this u equals cos theta into the equation. This is our rearranged radial equation. So we've got to do two derivatives of u. Let's just do the first derivative over here. Derivative of cosine is minus sine. And so the second derivative will be minus cosine. So we get minus a cos theta plus a cos theta plus b equals gm over h squared. Those two terms disappear, and we've come up with a condition for b. Now this is universal gravitation constant, 6.67 times 10 to the minus 11. This is the mass of the sun, and this is the angular momentum constant for the orbit, the square of that. So what I know then is that my orbit is given by this, where b is this constant. But of course the u variable that we picked was reciprocal r. So I put back in 1 over r, and now I have an equation for r as a function of theta. I know what b is, and I know that it's related to h, which is the angular momentum constant. Now, first of all, what does something like this look like? So let's, instead of a and b, just put numbers in there. 1 over r is 2 cos theta plus 3. Well, of course, theta is just going to do a lap, right? So when theta is 0, okay, so it's going to be 2 cos of 0 plus 3. And so 2 times the cos of 0 is 2 times 1 plus 3 is 5. But of course, that's 1 over r. So r will be the reciprocal of that. So it's 1 over 5. So when theta is 0, r is a fifth. All right. So now, at pi over 2, the cos of pi over 2 is 0. So that is just going to be 1 over 3. So it's bigger up here. Then I try pi. Cos of pi is negative 1. So this is negative 2 plus 3. It's 1. So this just ends up equaling 1 over 1. And then at 3 pi over 2, it's again a third. And at 2 pi, it's back to a fifth. So let me just tidy that one up because that looks really horrendous. And what I'm using here is, of course, 1 over r is 2 cos theta plus 3. So 1 over r is 2 times 1 plus 3. So r was a fifth here. There, that looks a lot tidier. Okay, so for the orbit, we get something sort of like this. That's really an ellipse if you plot it carefully. Okay, and we could put in any angle theta. We've just put in 4 or 5 special ones, but we could put in any angle theta and see how far our planet little m was from big M, because big M, the sun, is here at the origin. This is an elliptical orbit. Now, we'll see later that that's not the only type of orbit that you get, but it's pretty common. All the planets orbit the sun in elliptical orbits. And so that's nice because previously we just restricted our attention to circles, but now we know that orbits are really ellipses, and we've got the full equation now for the orbit. Now, let's say that that previous example, 1 over r was a cos theta plus b. That's our general form, and we were given that it was 2 cos theta plus 3 in our previous example. Let's say that instead of orbiting the sun, we were actually orbiting a neutron star, and let's get the h constant. Well, remember that our b constant here depends on that angular momentum constant, and it's 3. So we can solve for the h constant. It's going to be gm over 3 square rooted. So we put in the universal gravity constant. We put in the mass of the neutron star. We divide by 3, and we take the square root. And I get 4.7 units. And the units work out to be meters squared per second, because angular momentum units are kilogram meters squared per second, and then you divide by a mass, kilograms. So that would be the h constant for that orbit. Now, we've talked about b. Well, what about the constant a? Well, it turns out that that's related to the initial condition. If we define theta equals 0, or put the x-axis at the point of closest approach here, when it's in close, then that will be at theta equals 0. That will be the point of closest approach. Now, there's our angular momentum constant. H is r squared theta dot. But we know theta dot is omega. And at this point of closest approach, the velocity is going to be purely in the theta direction. So there will be no radial component at that point. So we can then define our velocity in terms of the angular momentum constant. So we know that h is r squared theta dot, but theta dot, you can see, is this velocity here, the v0, divided by r. So this is going to be r squared times omega, because theta dot's just omega, and that'll be the velocity over r. So that's r squared times the initial velocity over r. So that's just r naught v naught is our angular momentum constant. Okay, so now we can use that to solve for the a constant. We know that 1 over r is a cos theta plus b. So at theta equals 0, we'll say the r is r0 and the v is v0. We get 1 over r0 is a times the cos of 0, which is just 1, plus the b constant, which is gm over h squared. And we can solve this for a. So a ends up equaling 1 over r0 minus gm over h squared, and we know that h is related to the initial condition, r naught v naught. So the angular momentum constant at this point is just r naught times v naught, and this distance here will be r naught, the distance of closest approach, otherwise known as the perigee. So we can summarize that then, and that's summarized at the bottom of page 5 in the notes. Or right here it is. So here's the equation of a general orbit around the sun. And we'll see shortly that these can be circles, ellipses, parabolas, or hyperbolas. There's the b constant. In terms of the initial condition, that's how much angular momentum you've got. That's the b constant, and that is the a constant. So an example. So here we go. At closest approach of 1.75 astronomical units, so that's 75%, almost twice as far from the sun as the Earth, 75% further, because the astronomical unit is the Earth-Sun distance. So what we have, we've got a comet that's moving at the speed of 18,000 kilometers per hour. Now you'll see that I've skipped a couple of pages in the notes, and I'm now, I believe, up to page 9, doing an example. Just let me check on that. Okay, so false alarm. This is actually at the bottom of page 6 in the notes. So here we've got the distance of closest approach. It's 1.75 astronomical units, or in astronomical units, 1.5 times 10 to the 11. And it's orbiting the sun, and it's moving at, you'll see I changed this in the notes, 25,000 meters per second. Okay, so find the angular momentum constant. Okay, so at the point of closest approach, so here's big M, at the point of closest approach, the velocity is perpendicular. So the angular momentum, as we have argued, is just R naught V naught. So that's 1.75 times an astronomical unit times the given speed, and these are in meters and meters per second, and that works out to 6.5625 times 10 to the 11 meters squared per second. So this is an angular momentum, but it's angular momentum per unit mass, and it's a constant for the orbit. Okay, the constants B and A. So B is gm over h squared. G is the universal gravity constant, 6.67 times 10 to the minus 11. M is the central mass, which is the sun, and you divide by this h constant that we just discovered, and you get 3.0975 times 10 to the minus 12. So we know that 1 over r is a cos theta plus b. At theta equals 0, we've defined that as being our distance of closest approach. Cos of 0 is just 1, so A becomes 1 over R0 minus B. Just bringing the B to the other side and making cos of 0 1. So this is 1.75 astronomical units. That works out to 2.625 times 10 to the minus, or 10 to the positive, rather, 11. Then you subtract the B constant, and then you get for the A constant 7.119 times 10 to the minus 13. Now you can see what the units are for A and B here, or you can go through the dimension analysis. They're just reciprocal meters. So we now want to find the furthest distance from the sun. That's going to occur way over here. That'll be R far. And that's going to occur at an angle of pi. So I just take the orbit equation, and I put in an angle of pi. Of course, cos of pi is minus 1. So I just take negative of the A constant, add the B constant, and then do the reciprocal. And I can get the furthest distance from the sun. Works up to 4.19 times 10 to the 11 meters. If you divide by an astronomical unit, you can see it's a bit more than 2. It's almost 3. It's 2.79 AUs. Now, where we go next with this is we want to express A and B, learn something about A and B in terms of the type of orbit, because we've said there are these 4 types of orbit. And in order to do that, we're going to introduce a parameter known as the eccentricity. The eccentricity will be a Greek letter epsilon, and we'll define it in terms of, these are some conic section terminology, the distance from the focal point to the curve divided by the distance to the directrix from the curve. And you can think of the eccentricity as how far away is it from being a circle, okay? Because it's going to turn out that the eccentricity of a circle just ends up being a 0. And then for an ellipse, it ends up being between 0 and 1, and for a hyperbola, it's bigger than 1. More on that later. But we'll take it to this point in the notes, and then we'll pick it up at this point in class, because we want to do a derivation and see how the eccentricity relates to the A and B constants.